In this video, we're going to talk about how to calculate the mass defect of an isotope and also how to calculate the nuclear binding energy per nucleon. So let's start with this problem. What is the mass defect of carbon-12? The mass defect is the difference in the mass of the nucleus and the mass of the individual particles that make up the nucleus. So let's talk about carbon-12. Carbon-12 has a mass of 12 and an atomic number of 6. The number of protons is equal to the atomic number. So carbon-12 has 6 protons. The difference between the mass number and the atomic number is the number of neutrons. So 12 minus 6 is 6. Now for an atom, the number of protons and electrons are the same. An atom is electrically neutral. So an atom of carbon-12 has 6 electrons. Ions have different numbers of protons and electrons. Now let's calculate the mass of the nucleus separately. The mass of the nucleus is the difference between the mass of the carbon atom and the mass of the electrons in that atom. So we said that carbon has 6 electrons. Now let's calculate the mass of the carbon atom in kilograms. Let me do this at the bottom here. Now, the atomic mass of carbon is 12 AMU, 12 atomic mass units. And you need to know that one atomic mass unit is 1.66054 times 10 to the negative 27 kilograms. And you can look that up in the internet. It's not hard to find. Just type in AMU to kilograms in Google or something, and it should come up. Now let's go ahead and multiply those two numbers. So the mass of carbon in kilograms is 1.99265 times 10 to the negative 26 kilograms. And then minus 6. Now the mass of the electron in kilograms is 9.11 times 10 to the negative 31 kilograms. Alright, so let's go ahead and plug this in. So the mass of the carbon nucleus is 1.99210 times 10 to the negative 26 kilograms. So notice that the mass of the electron is relatively insignificant. If you look at the difference between these two numbers, they're almost the same. 1.99265 versus 1.99210. So let's say if you decide to neglect this value, your answer shouldn't change too much, but if you want to get the exact answer, subtract the mass of the carbon atom by the number of electrons present. So now that we have that, let's get the other stuff, the mass of the particles. So we said that carbon-12 has 6 protons and 6 neutrons. So the mass of the particles is going to be 6 MP, 6 protons, and 6 Mn for neutrons. So we have the mass of a proton, and here it is. So that's 1.67262 times 10 to the negative 27. A lot of numbers to write down. And then we have the mass of a neutron, which is a little bit heavier than a proton, but it's almost the same. Alright, so let's figure out what that's going to be. So if I typed in everything correctly, this is what I got. 2.00853 times 10 to the negative 26 kilograms. So hopefully you got that too. So now we can calculate the mass defect. So the mass of the nucleus, that's 1.9921 times 10 to the negative 26 kilograms. And then the mass of the individual particles that make up the nucleus is this number. And so let's see what this is going to be. So this is going to be negative 1.643 times 10 to the negative 28 kilograms. So that's the difference between the mass of the carbon nucleus and the mass of the individual subatomic particles that make up the nucleus. So that's the mass defect of carbon-12. Now let's calculate the nuclear binding energy per nucleon. So we need to use this equation. Delta E is equal to delta mc squared. So the mass defect is this number. C represents the speed of light, which is 3 times 10 to the 8 meters per second. And then we have to square that number. So the change in energy is negative 1.4787 times 10 to the negative 11 joules per individual nucleus. Now you might be wondering, why is this answer negative? Now what this means is that if you take the 6 protons and the 6 neutrons and put them together to form the carbon nucleus, energy will be released since mass is lost. So what really happens is the mass is converted to energy. So as those 6 protons and 6 neutrons come together to form the nucleus, that change in mass, that difference in mass, was converted into the energy that was released by that process. So that's why it's negative. Now the reverse is positive. Let's say if you have a carbon nucleus, it's going to take this much energy to break the nucleus into its individual particles. So the sign depends on what you're trying to do. If you're trying to bring the particles together to make up a nucleus, then energy will be released. Delta E will be negative. If you're trying to put in energy to break up the nucleus into its individual particles, then delta E is positive. Now to calculate the binding energy, the energy that we need to break the nucleus, that's going to be a positive value. So we need to calculate the binding energy per nucleon. Now you need to know what a nucleon is. What do you think a nucleon is? A nucleon is basically a particle in the nucleus. So protons and neutrons are considered to be nucleons, not electrons. So carbon-12 has 6 protons and 6 neutrons. So 6 plus 6 is 12. So we could say that it has 12 nucleons. So to calculate the binding energy per nucleon, the nuclear binding energy, it's going to be this value. Well, let me convert it. So let's start with this number. This is the energy per nucleus. And one carbon-12 nucleus has 12 nucleons. And so the unit nucleus cancels. And so now we have the joules per nucleon. And so this comes out to be 1.232 times 10 to the negative 12 joules per nucleon. So that's the binding energy per nucleon. Now, sometimes you may need to report your answer in mega electron volts per nucleon. If you need to do that, you can use this conversion. 1 mega electron volt is 1.6 times 10 to the negative 13 joules. So the unit joules will cancel, and let's go ahead and divide these two numbers. So you should get 7.7 mega electron volt per nucleon. So that is the nuclear binding energy of carbon-12. That's all you need to do. Number 2, calculate the change in energy in joules and mega electron volts if 5 moles of nitrogen-14 nuclei were formed from protons and neutrons. So if you want to try this problem, feel free to pause the video and work on it. So let's begin. So we said that the mass defect is the difference between the mass of the nucleus and the mass of the individual particles that make up the nucleus. So in this case, we're combining protons and neutrons to make up the nitrogen nuclei. And so energy is going to be released when that happens. Anytime a bond is formed between two atoms or two particles, energy is released. So we should expect a negative energy value for our answer. Now let's calculate the mass of the nucleus first. So it's going to be the mass of the nitrogen atom minus the 7 electrons that are in the nitrogen cloud. Now keep in mind, nitrogen-14 has an atomic number of 7. So it has 7 protons, 7 neutrons, and also 7 electrons. The number of neutrons is going to be 14 minus 7. And for an atom, the protons and electrons are the same if the atom is electrically neutral, which by definition it is. Now let's calculate the mass of the nitrogen atom. So we're given the mass in atomic mass units. So that's 14.00318 MU. Now based on our last problem, we know that one atomic mass unit is 1.6605 times 10 to the negative 27 kilograms. So that's not going to change. And so the mass of the nitrogen atom is 2.32527 times 10 to the negative 26 kilograms. And then the mass of the electron is 9.11 times 10 to the minus 31 kilograms. So let's go ahead and plug that in. So you should get 2.3246 times 10 to the negative 26 kilograms. So now we need to calculate the mass of the subatomic particles in the nucleus. And so we said that nitrogen-14 has 7 protons and 7 neutrons. So the mass of a proton is 1.67262 times 10 to the negative 27 kilograms. And then the mass of a neutron is 1.67493 times 10 to the negative 27 kilograms. So you should get this number, 2.343285 times 10 to the negative 26. So now let's go ahead and use this equation. So the mass defect is the difference between these two numbers. So if we subtract 2.32463 times 10 to the negative 26 by 2.343285 to the same power, you should get negative 1.8655 times 10 to the negative 28 kilograms. So that is the mass defect in this problem. That's the change in mass. So when the 7 protons and the 7 neutrons get together to form the nitrogen nucleus, this is how much mass is lost. And so that mass is changed into energy. So now let's calculate how much energy is released during the process. So this is going to be negative 1.8655 times 10 to the negative 28 kilograms multiplied by the square of the speed of light. And so the change in energy is negative 1.679 times 10 to the negative 11 joules. And this is per nucleus. So that's how much energy is released if only one nucleus is formed. What about if 5 moles of nitrogen nuclei were formed? How much energy would be released? Let's start with 5 moles. Now, 1 mole is equal to Avogadro's number, 6.022 times 10 to the 23, and we're dealing with the nitrogen nuclei. And the energy change for just one nucleus is 1.679 times 10 to the negative 11 joules. And so we can see the unit moles will cancel, and the nucleus will cancel as well. So this will give us the energy change in joules if 5 moles of nitrogen nuclei were formed from protons and neutrons. And so this is equal to 5.055 times 10 to the 13 joules. And so that's the answer in joules. Now, if you want the answer in mega electron volts, simply convert it. Divide it by 1.6 times 10 to the 13 joules. Okay, that's supposed to be a J. So if you're wondering why the sudden change in the screen, that's just me editing this video. Because I made it before, but I noticed that I missed the negative sign. 1 mega electron volt is not positive 13, but it's 1.6 times 10 to the negative 13. And so I had to correct that mistake. And so the answer that you should get is going to be 3.16 times 10 to the 26 mega electron volts. So one little negative sign can change your answer drastically. So that's the answer that you should have. And so that's it for this video. Thanks for watching, and have a good day.